Hello everyone. Today we are going to go through the steps needed to predict the products of 3 of the 5 types of reactions. Combustion is pretty straightforward because the products are always the same, but today we're going to learn how to predict the products of single replacement, double replacement, and decomposition reactions. These can be added in to the back side of your types of reactions note sheet. If it's a little tight on space, do what you need to in the right column to make sure that you have room for all these steps. Now for our replacement reactions, we have some reference sheets or some tools to help us determine whether the reaction will happen or not. For single replacement, the activity series is this tool. It is a list of elements, either all metals or all nonmetals, that gives us a range of the reactivity of those elements. The higher it is on the list, the more reactive it is. The lower it is on the list, the less reactive. We will only ever be comparing like elements. You always reference a metal against a metal or a nonmetal against a nonmetal. You will receive this sheet as a resource to use on tests and quizzes. So if we look here, we see that the metal list is quite a bit longer than the nonmetal list because there are more metals on the periodic table. Now, our steps to follow. The first thing I have to decide is what is the singleton, the element that is by itself as opposed to bonded in the compound. That's going to tell us which activity series to use. Then, once I've decided that, I look at the activity series and compare the singleton to its comparable element in the compound. What I really want to make happen is the most reactive thing, the higher thing on the list, will be the one that's going to end up or stay in the compound. So if the more reactive element starts by itself, it's going to trade places and move into the compound, and the less reactive element will then become by itself. If the more reactive element is already in the compound, it will stay there and no reaction occurs. So here, when we look at these examples, calcium plus lithium chloride is what I'm considering as a possibility. Calcium is a metal, so I'm going to compare it to the lithium metal in the compound. Now looking back at my sheet, I'm going to find calcium and lithium on the chart. They are visible right now. Lithium is higher than calcium, meaning it's more reactive. Since it is already in the compound, it's going to stay there. Think of it that calcium doesn't have enough ability to knock the lithium out of its place. In this case, no reaction would occur. In the next one, sodium is a metal, so I'm going to compare the sodium to the aluminum. Sodium in this case is higher than aluminum. So, too far, wrong way. So the sodium being more reactive is going to trade places. This is where I now have to do a little bit of work. So now the sodium is going to bond to the carbonate. Na makes a +1 charge, and the CO3 is a -2. And then the Al would be by itself. Then, as always the case, I'm going to finish by balancing the reaction. The aluminum would be solid, and the sodium carbonate, the Na2CO3, would then be in solution. Now, you guys can try the last one on your own and practice that using the activity series for yourself. Now, if I'm looking at double replacement, one of the things we learned by doing our lab is that sometimes you'll get a precipitate formed and other times you won't. So we're looking at whether a solid forms when I originally had 2 clear solutions. But really the difference is, do I have a new substance? We said forming some other state of matter is an indication of that. So the rules can be presented in a couple different ways. It can either look like this chart, where we find out what happens when we mix those ions together, or it's a set of rules that we can follow that are statements that we can work through in order. Today we're going to use the chart as a way of looking at this. So please make sure you pause the video at this point and write down these steps to follow. The products, it's easiest to do it where you actually make the switch and form the correct substances. Then we can go back and compare and see if you would get something other than an aqueous solution. If both compounds that potentially would be produced remain aqueous, nothing happened. They are in the same form that they were before. But if one of the compounds appears to create a solid, liquid, or gas, a new substance, then we would have evidence of a chemical reaction. Because this depends on state of matter, this is the most important type of reaction to include this in the equation. So let's look at an example. So, had a little bit of jumbling there, but we're going to take a look at an example here. So when I look at NaNO3, sodium nitrate combining with magnesium bromide, I'm going to make the switch right away. The sodium would now be with the bromine. And the magnesium would be with the nitrate. Those are what I'm now going to go check on my chart. So when I take a look at the chart, you'll see the left side, the metal, is organized by alphabetical, and then across the top we have our ions. So first I'm going to find sodium combined with the bromine. This product would be aqueous. We see that it's still in the dissolved state. Now I'm going to check the magnesium and the nitrate. So I find magnesium and across to the nitrate. Both of these would create aqueous substances, so when we go back to our problem, there would be no reaction. Now in the second one, I see CaCl2 combining with lithium 2 sulfide. So I'm going to take a look and make calcium sulfide. And I'm going to check those on my list. Now I know it's probably a little tiny on your side, but the calcium sulfide does produce a solid, so we know this reaction would happen. Since that's the case, I mark the calcium sulfide as a solid, then I complete by balancing the equation. Predicting the products of combustion reactions are pretty straightforward, as long as you can recognize that you have something with C's and H's, possibly an O, combining with O2, the products are always CO2 and water. So simply fill them in and then balance the equation. I will leave that to you guys as a challenge problem. Lastly, decomposition is breaking apart of substances. You will be provided with a set of rules, either in a cloud format, where it's a series of identification based on what your starting substance is, but I also have it written out as a series of steps to follow or an explanation of what occurs. So take a moment to write down what you see here as kind of your rules. It's if this is what I have, then this is what occurs. So you're going to have to do decomposition of binary compounds, oxyacids, any hydrogen bonded to a polyatomic ion with an oxygen, metallic carbonates, chlorates, and hydroxide. So if I have any metal bonded to one of those, it will simply follow a pattern, and then you apply what happens. So if I look at my CaOH2, Ca is a metal, and OH is hydroxide. So I'm going to follow the rules for metallic hydroxide. It tells us I'm going to break apart into the metallic oxide with water left over. So calcium is going to bond to oxygen, metallic oxide. And Ca is a 2 plus, O is a 2 minus, so they balance out based on their charges. When I take a look at the KOH, I have a metallic hydroxide as well, so it'd be the same situation. Please note, I'm not balancing these, but I'm showing you what the formulas should be. Our last example would be an oxyacid. Here we see hydrogen bonded to sulfate. We see that I'm going to make water and a non-metallic oxide. The trick for this is I'm simply going to remove the atoms I need to make water and record anything else that's left over. So if I take away 2 H's and 1 O, that leaves SO3 behind. To be paired with the water. So as long as you can identify the reactant, you simply have to apply what it tells you to break it apart into as the products. You can use these as examples as you work through the practice problems in class.